very much for being here and coming this morning. Thank you to the analytics section for the opportunity to participate in this award. We certainly appreciate it. In academia, we often disseminate our work through very traditional means, which are publications. But over the last several years, our own research group has decided that there are other avenues which we can, in fact, showcase our work and give people the opportunity to appreciate academic research, and in particularly analytics academic research, in a manner which is friendly, which is innovative, which is informative, and hopefully which is fun. And in particular, this project, which is BracketOdds, is a joint effort involving a number of people. Doug, you were here somewhere, Doug King, who was one of my PhD students who graduated not long ago and now is a visiting lecturer in the Industrial Engineering Department in Illinois. Alex Nikolaev over here, who is also a former PhD student, who is now at the University of Buffalo, and Adrian Lee, who's also a former PhD student, who now runs the center, Cyturi. Now, how many people are familiar with March Madness? Oh, I'm preaching to the choir. How many people do a bracket? A number of people. Now, why don't you pass me your basketball? There we go. In my younger years, I played a little bit. Now, from my height and stature, do you think I played center or guard? Now, BracketOdds was an idea that grew out of an academic effort. It's not something that we said was our goal, but everything we do ultimately has to have some academic value. And we created a tool so that the average person can actually take advantage of it. Now, Peter Keating is a writer, a senior writer for ESPN, the magazine. And he is a strong advocate of sports analytics. And I've had the opportunity, in fact, to let him know about our site and what we do. So what I'm going to do over the next 20 or so minutes is give you an idea of the motivation, as well as what went into creating this website. And then I'm going to show you the website and show you some of the functionality that it provides. So next March, when you're penciling in your bracket, you will have a place to go to help you determine, in fact, whether, in fact, you've put together a reasonable bracket. Now, given that fact, I'm going to give a very brief history of the tournament so that everyone who maybe, most of you are familiar with it, in case you aren't. The NCAA men's basketball tournament is truly one of the great sporting events in the United States, if not the world. Certainly one of the top five. And it's been held actually for quite a while. It dates back to 1939, which most people may not be aware of. But it only involved 8 teams at that point. And of course, things have grown since then, a lot of it motivated by economics. And in 1985, it basically was thrust into what we consider to be the modern era of the tournament, which is the 64-team tournament. And that tournament now increased to 68 tournaments with 4 play-in games. So you have the so-called first 4 leading up to the final 4, which is a nice play on words. Now, what drives a lot of the popularity, of course, is wagering and gambling. Billions of dollars are wagered on the tournament each and every year. And as a result of that, everybody wants to be able to pick the perfect bracket. Now, with 68 teams, and let's bring it down to the 64 after the first 4, you have basically 63 wins, and if you believe they're all equally likely, which they are not, then 1/2 to the power of 63 will give you a very large number. So the chances of picking that perfect bracket, of course, are very, very small, purely by chance. Now, bracketology. Does anybody know who the professor of bracketology is? Joe Lenardi is Dean, the professor of bracketology. The Chicago Tribune wrote an article about our work a few years ago, and since I'm a professor and I do bracketology, they put the 2 words together. I don't think Joe was insulted, though. I think he was just fine with that. But basically, everybody tries to put together the perfect bracket, and seedings are, in fact, the driver. And when you have a team that is seeded number 1, and you have a team that is seeded number 16 in a particular region, beat the 16 team. And that has happened consistently since the beginning of the tournament. So what did we want to do? We actually did some research based on analyzing seed positions. And we wrote a couple of papers, which we published in academic journals, which looked at these and tried to, in fact, weed out patterns that existed in how the seeds propagated through the tournament. And little did we realize that there are such patterns. a very well-defined pattern, which can help people design their brackets. The next natural step was to say, well, what can we really accomplish? So we realized that we can accomplish exactly the things that what we try and do in analytics, which is we want to be able to describe the past performance of each seed. We want to be able to predict the future winners based on this past performance. And then lastly, we would like to prescribe the most likely brackets for you, the people who are putting together your brackets, should use. Because there are some brackets that make no sense. There are other brackets that are very, very likely to occur. And then, of course, we can validate all these results by looking historically at what happened and looking at how often, based on what we think should happen, did happen. And it gives us a very simple way to do the validation. So what is aligned with the analytics mission is very consistent with what we intended to do with our bracket website. Now, with the tournament structure, and this is very critical because teams are given seeds, and these seeds contain information. And this information has to be used intelligently to create, ultimately, our model. The selection committee puts together at-large teams as well as teams that win their conferences, and together we come up with all of the teams, which are 68, including the 4 play-in team games. Everybody's assigned, after the play-in games are done, seeds 1 to 16 in 4 different regions. And there's other factors that are taken into account based on geography. So typically, if you're a very good seeded team, one of the higher seeded teams, and you're in the East, let's say in North Carolina or Duke, you'll tend to play in the East or in the Southeast. While if you're on the West Coast and you have to be a good team like USC or UCLA, then you'll tend to be in the Western region. They try and do those things for the better teams to make travel a little easier and give them some advantage because they've earned that advantage. The format of the tournament is single elimination. And basically, as you propagate through the tournament, you ultimately are forced to play better and better teams. So here's a picture of one of the regions. Team 1 will play Team 16, Team 8 will play Team 9, and so forth, and then the winners will play each other until eventually you have the winner of each of the regions. You have 4 regions, and it comes down to the so-called Final Four, and the ultimate winner is returned from that. And here we see, in fact, if only the better seeds won, we would see how the propagation of seeds would go, and eventually we end up with, in this case, the best seed won the region. Very simple. It's a very simple single elimination structure. Once we get to the Final Four, though, we take each of the 4 regional winners. They will play each other. Typically, there's been designated a top region, a second best region, a third best, and a fourth based on the number 1 seeds, and they will play each other until we eventually have a winner. Now, that's how the tournament works. What did we do with our model? We made a hypothesis that we could create a model which would enable us to see and understand how the seeds will propagate through the tournament. Not the teams, the seeds. Because we believe that the teams are less relevant than the seed. What's more important is how you let the seeds move through the tournament, and then you affix a team to that seed. And interestingly enough, research has been done. In fact, one of my colleagues at the University of Illinois actually did an experiment with this. He's an industrial psychologist. And he had people before the last tournament put together brackets based purely on seeds and put together brackets purely based on the teams. And they were statistically indistinguishable in terms of their performance. If that wasn't true, our model couldn't work. So in some sense, what he did was validate, without realizing it, that seeds drive everything. So as a result of that, we hypothesized the model, and basically it was based on a truncated geometric distribution. Now, why the truncated geometric distribution? Well, it was an idea. We played with some data, and eventually we made this observation. But a very nice feature of the geometric distribution, and the exponential distribution also possesses it, is the memorylessness property. And this memorylessness feature is really what seems to be the fact that drives the validity of the model.
Memoryless of what?
The memoryless property.
Of what?
Of the random variable. There are certain random variables that have a memoryless property which is defined mathematically or probabilistically. And
no, what do these random variables represent?
Oh, we're going to talk about that. With this, what we're going to do is we're going to look at how the seeds are defined, and when they play each other, how far they're going to go in the tournament. So what we needed to do is look at which teams can potentially play each other in each round, rank them based on their order, and then the likelihood that that seed, the best seed, would escape would be determined by a truncated geometric distribution. So if a geometric distribution can take on the value 1, 2, 3, and so far, if we truncate it to 4, and we're looking at 4 teams, with a certain probability P, we will then have the first one being picked. If not the second, the third, and the fourth. So the truncated distribution gives you the distribution of the seed position that will propagate through the rounds. Now it turns out to validate that is very hard. But Alex's contribution was to find a relatively obscure theorem which would give us the result we needed that we can validate it within the framework of the tournament. That was the beauty of this result. So basically, we, at every single round, look at the sequence of seeds, which we call sets, and then we apply this truncated geometric distribution to see if the first position, second, third, fourth, when you go down to the fourth round, it's all 16 that will occur. And the simplicity of this model, which is what in fact we wanted, is to enable us to take this, introduce it to a very wide audience, assuming that we're able to package it well, and allow people to actually use it to see where their seeds will fall in the tournament. The wonderful thing is, since 1985, we have all of this data that we can validate the results. So from 1985 to 2012, there have been 1,638 games. We've eliminated the play-in games because in the first 4 games, because they just aren't relevant to the structure. We didn't want to change the structure. And it gave us the opportunity to do the validation. Now, just to give you a picture of this, and this is an example, in the third round, if we look at the set 1, 8, 9, and 16, so those are the teams that can possibly advance that far. If the parameter for this truncated distribution is P, then the probability that seed 1 will be the winner out of that group would be P. Seed 8 would be P times 1 minus P. Seed 9 would be P times 1 minus P squared. Seed 16 would be P times 1 minus P cubed. And then we scale it all so that the total probability is equal to 1. Now, if P is very close to 1, this seed will always come out of that group. If it's smaller than 1, there's a chance that the 8 or the 9 or the 16 could occur. So what this does is it gives us an iterative process which will enable us to pick seeds as the tournament progresses. Very simple idea. Now, how do you get this P though? Well, what we did is we basically used the method of moments based on this historical data, and I have it all set up in a spreadsheet. And it will change from year to year because every year when we get new data, I have to recalculate and recalculate all of these p-values, which I do. And I'm the only person who has that spreadsheet. So you can take this model, you can fill the paper, but unless you have the special sauce, which is the P, you can't run the model. And we have that special sauce. Let me give you some idea of what we can compute. So this is in the final 4. We looked at all the seeds that have appeared in the final 4, the number of times they actually appeared, and based on our model, how many times we would have expected them to appear over the last 28 tournaments. And then we looked at the delta value, which gives us basically the chi-squared goodness of fit component. And we wanted to make sure, in fact, does this fit well? Now, as a result of this, we're able to then provide a mechanism to say, okay, this model is reasonable, what else can we compute with it? And this is when we get into the more prescriptive aspects, because we can compute probabilities of events that have never occurred. We can do things that people say, well, historically, have we observed this? No. That means it's never going to occur. Not necessarily. It means it just hasn't occurred yet. And that's exactly what our tool is designed to do. So here's an example of data where if we look at the final 4s, how many times have we observed 0, 1, 2, 3, or 4 number 1 seeds in the final 4? We can compute these probabilities using our model. We can then look at the expected number of occurrences over the last 28 tournaments, and then we can actually say, well, how many times have we observed this? Well, we actually observed
no number ones, only twice. We expected it to be 4.2. We had 11 occurrences of Final Fours with one number one seed, but we expected a 10.2. And the list goes on. And you can see that these numbers are certainly well within reason. Now what's surprising is people always like to choose their number ones, but we only expect it less than one time every 28 years. In fact, approximately once every 48.6 years. Yet, and we've only observed it once. It's the least likely combination. Yet intuitively, you think it's the one that's going to occur. A little hint for your bracket. We also are able to compute the likelihood or probability of every single seed combination that has ever occurred. And we've ordered them here from most likely to least likely. The most likely combination is 1, 1, 2, 3. It's occurred 3 times and it has the highest probability. And the list goes down. 1, 1, 2, 1, 1, 2 is the next most likely. And the least likely occurred, in fact, not that long ago, in 2011, where we had 3, 4, 8, 11. Does anybody remember the teams? Butler? Kentucky?
Michigan State,
Connecticut?
and
VCU.
And VCU, exactly. Connecticut, Kentucky, Butler, and VCU. The likelihood of it occurring was, as you can see, 1.4 times 10 to the minus 5. It should occur approximately every 70,000 years. And it occurred. Before that, the least likely was 1588 in 2000, occurring approximately every 21,000 years. So you get an idea of what we're capable of computing. We also can compute things that are just interesting facts and anomalies. What's the probability of having one or more 16 seeds in the Final Four? It's around 0.0012. It should occur approximately once every 828 tournaments. And you can go through, how about one or more 15 or 16? One every 318 tournaments. One or more 14, 15, and 16? One every 160 tournaments. These haven't occurred yet. 13, 14, 15, 16? One every 88 tournaments. 12 or worse, 51 tournaments. And here's the magic 11, which we've seen 3 times now. It should occur once every 31 tournaments. Very reasonable, and we observe it. So as a result, we can compute things that nobody's been able to do. What about all 16s? They've never won a game. What's the likelihood that they're actually going to, all of them, make the Final Four? Well, the odds are 121 trillion to 1, basically. The probability is 8.29 times 10 to the minus 15. Close to 0, but not 0. How about no teams 1, 2, or 3 being in the Final Four? 303 to 1, never occurred. How about no teams 1 or 2? It should occur approximately once every 45 years. It occurred in 2011, only once. So you get an idea that the data is consistent with what the model is producing, which of course is what we wanted to achieve. We looked at the last tournament and said, well, gee, how does this compare to what people are doing in competitions? And if we look at what happened in 2012, where we had 1, 2, 2, 4, which was Kentucky, Ohio State, Kansas, and Louisville, the odds against that occurring were 523 to 1. We're able to compute that. Now, CBS Sportsline has a tournament where you can sign up. Has anybody taken part in it? No? A few people. And they had over 5 million entrants. The number with this was 17,979. With our model, we would have expected actually just half of that. Within an order, certainly well within an order of magnitude. So what are the conclusions and limitations to discuss? We've created a model based on analytics. It's simple enough that it can be understood, but it's powerful enough to create results that can be used. Now, the other thing that we've tried to do is make sure that it is mathematically rigorous. So we've gone through the appropriate validation process. But we also want to make it informative and interesting. And that eventually led to the creation of our website, which I'm now going to show you in the next 5 minutes, called BracketOdds. And choosing a name is always important. So we came up with BracketOdds, and this is the website for it, bracketodds.cs.illinois.edu. And I basically was able to recruit a couple of undergraduate students, both of which really like basketball. It really helps to like basketball. And what they did is I said, here's the model. We're going to transform this model into a user-friendly tool and launch it and see what happens. So let me tell you a little bit about the functionality before I show you the website. It basically enables you to look at the last 4 rounds, which is the Elite 8, the Final 4, the National Finals, and then winning the National Championship, and compute the odds against these occurring. You can also compare the relative likelihoods of different seed combinations, and you can even compute conditional probabilities in the last 2 rounds. So there's a variety of things that you can do. The other thing I will note is that the website only has a small fraction of the capabilities of the model. So when we're approaching March Madness, I'll often get either emails or calls from sports writers who see our website and say, how would I compute this? And I'll say, no, give me 5 minutes, and I'll go and I'll compute it offline because the website can't do everything, but certainly the model can do just about anything. And I compute their probabilities and then they report it. Now, I'm going to show you the website right now. I have it set up here, which will give you a little feel of its functionality. And there we go. BracketOdds. And it has a basketball feel to it. It's a basketball court. And it has a variety of things. I'll take you through a few of them. I won't be able to take you through all of them. But it has some information, a little bit of tournament background, the probabilistic analysis. It also gives you some references. We also have an added point that we just added last year, which, information you need to know to help you build your bracket, some tips. And here's the table I showed in the presentation, just some information that's useful for people putting together their brackets based on our analysis. The other thing that you can do is you can go in and let's take the Final 4. You can actually put in any seeds, so the odds against 4 number ones would be 48.7 to 1. If we want to change this, so let's put in a 1, a 3, a 5, a 2. The odds against that occurring are 55.49 to 1. And the other nice thing you can do is if you're trying to make choices in your bracket, so for example, take a 1, 1, 2, 3 versus a 1, 1, 1, 1. I said that 1, 1, 2, 3 was the most likely. In fact, it's 2.9 times more likely to occur than a 1, 1, 1, 1. It's in fact occurred 3 times, 1, 1, 1, 1 has only occurred once. So it's certainly consistent. We can do anything we want in terms of combinations. In fact, sometimes what we can do is rather non-intuitive. So 1, 1, 2, 2 versus 1, 1, 2, 5, well, let's make this one a 3. Which one's more likely, 1, 3, 2, 2 or a 5, 1, 2, 1? And it turns out the 1, 3, 2, 2 is slightly more likely to occur than the 1, 1, 2, 5. So this gives you the opportunity to put in information and come up with a sense of whether your bracket is so far off that it's highly unlikely to occur. We also have this, if we go down to the National Finalists, same idea. You can get the odds of the seedings. The seedings against 2 number ones are 4.366 to 1 against. If we put in a 1 versus a 5, it's much rarer. We can compare also. So let's put in a 1, 2 versus a 1, 4. And the 1, 2 is around 3 times more likely than the 1, 4. And here's the conditional probability. So you can set up your bracket with different seeds in the 4 regions. So you have a 1 playing a 3, a 2 playing a 1. And this tells you the likelihood of who's going to come out of those regions. A 1 versus a 2. A 1 versus a 1, a 2 versus a 3, or a 1 versus a 3. So once again, it gives you the opportunity to use the analytics that we have in a user-friendly manner and come up with results that will help people determine whether, in fact, their bracket is so far off that they're really trying to roll the die, or come up with something that's very conservative. And it gives you the opportunity to be able to do that. Well, I can go on for hours on this because I like it. It's a lot of fun, but I think we'll stop at this point. Thank you very much.
Thank you.